All right. Thank you very much for this introduction. So welcome everyone. It's really great to be here, even with this virtual environment. My name is Alex. I'm working for Google Warsaw for a year now, and I'm part of a Borg engineering team. And today I would like to talk a bit more about development, review, integration systems that we're using at Google to do our everyday job. Google is it's a pretty interesting place with a lot of systems around and working at pretty interesting scale, and it requires working in a very specific way. So I thought that sharing the experience I had during the last year while getting to know all of those systems and what are the goals behind those systems, like what do we try to achieve, would be very interesting for everyone. So without further ado, let's switch to agenda. So it's going to be split into three main points. So the first point is the goal. What do we want to achieve and why we want to achieve that? So we're going to discuss, what's our end game in terms of where we want to be with our development systems and why. Then we will discuss the most important problems that are on the way, and those problems are pretty specific to Google sometimes. So it's rather interesting to see those kind of problems, and then basically the solutions that Google deploys to maintain engineering productivity. And then we'll have a bit of a question and answers for everyone to be able to reach out with a question. So if there are going to be any, I'll be happy to answer. Okay, so first, the goal. So first of all, like why do we care, right? What's the point? So Google as a company is a place where we're really striving to maintain a very high engineering excellence ecosystem, right? So we're always trying to do the best thing. We're trying to adhere to the best practices, and we're really working hard to preserve this strong engineering culture. And this has some practical consequences, or it's more about the fact that engineering excellence by itself leads to higher productivity for each engineer working at Google. So working at the scale we're working usually at makes us not able to employ certain workarounds to move with the work forward. We really have to strive to do the best thing at all times, and make sure things are consistent at every step, and that they're working fast, and that work with all of those internal systems is progressing at appropriate pace, because otherwise you'll get blocked all the time. So as such, engineering productivity per se is like a very high priority for Google, right? We've got teams who are working on this. We've got we've got many teams which are working on different systems which are supporting our engineers doing many things, ranging for coding, testing, integration testing, review, deployment, many other things. Okay, so I took a quote from a mission statement from one of our teams, which is engineering productivity, right? So the quote is like this: accelerate Google engineering excellence and productivity at scale. So I think like personally, I think two important things are coming from this quote, like productivity and scale. So you know, first thing, like as I said, like excellence, engineering excellence, and doing the right thing directly translates to productivity of each engineer. And it relates to the scale in a way that if you wouldn't do the right thing, it would get to, you know, it would come back to you with some sort of problem real fast. So I think it's really important that, you know, we as Google engineers try to strive to do for the best thing always. And I suppose that's why we're putting that much, you know, that much emphasis on those internal systems to make sure that, you know, they're doing the right thing. So the goal, like what it actually means to do the right thing. So first of all, you know, next time it will be easier. So joining Google and in general working at Google with Google systems has some degree of learning curve. There's a lot of them. There's, you know, some degree of complexity to it. So you know, making sure that this learning curve is not as high is very important. It makes, you know, people who are joining get on board faster, and for people who are already onboarded or, you know, are veterans, it makes their work easier. And you know, things are always evolving. So you know, when things are easy to adapt to, it's you know, it's much easier for the people to actually be able to work with those systems, right? We don't want to have people, you know, having to spend like a lot of, you know, sort of mental capacity in order to be able to use those tools. The next step, it will be faster. So this directly relates to, you know, to scale, to, you know, how much code there is, to how much tests there are, how, you know, how many systems there are. So basically, it's really important that each of the actions, right, that you take while developing some kind of software artifact, right, be it code, be it you know, a reviewable CL, or, you know, sort of a pull request, right? Or I don't know, a deployment, or you want to run some testing, wherever. It's really important that you don't get blocked for too long, like that, you know, you're not waiting, I don't know, 20 minutes or 30 minutes for the build, or you are not waiting, I don't know, two hours for all the tests to pass. You need this quick feedback loop, right? And for this quick feedback loop to close, you really need things to move fast. So this, you know, this is challenging when you're running at the size this big. And also the next time it will be predictable, right? So again, the problem with running at that big scale is that sometimes things are not, you know, 100% deterministic, right? You've got flaky tests, you've got, I don't know, some subtly induced bugs. So it's really important that, you know, all of the systems that are used for development are as predictable as possible, that there, you know, there are no unpleasant surprises that you have to debug, because, you know, it takes a lot of capability, you know, a lot of mental capacity of you. It takes a lot of time, and, you know, because each of the engineers is actually busy with, you know, with their own problems and whatever they're trying to solve, you know, it's decreasing their velocity and their productivity a lot. Okay, so that's basically the goal, right? We want to have systems which are fast, which you know, you can call multiple times and nothing changes, that they're predictable. You want to make sure that they're easy to work with, and you want to make sure that all of this works for everyone. So this is like the main problem, right? So first, the scaling up. Google, you probably know that, but Google has a high engineering population. There's a lot of engineers at Google. So it's also important to know that Google has a very large code base. There's a lot of code. I'm not going to share any metrics, but there's a lot of code. And This presents a lot of challenges that are not usually seen in various organizations which are smaller or are seen to a limited extent, but we have to tackle, on everyday basis. And it also drives or has driven certain decisions in terms of how we work on every day. Right. So obviously the problem number one with scaling up is performance. So when we've got a lot of engineers, we've got a lot of systems which are being called, and basically this means that each of those systems becomes a service per se, right? So I don't know, we're talking version control system, we're talking, I don't know, tools to review, we're talking, I don't know, IDE, whatever really. It's going to be a service by separate, like it's like a separate service like any other, and it has to serve its traffic reliably, and it has to provide some guarantees. It has to be, in case something breaks, it has to be fixed fast. So basically it incurs a lot of work around each of those subsystems. Okay, so another interesting point that I found really interesting to work with is the problem with integration of code and code reusability. So first, I should probably say that before I joined Google, I was actually in habit to do very large, like, PRs, pull requests. Like, I was developing code, I was doing some kind of a feature and I would merge it after some time, right? This is very hard to do at Google. And the reason is because at engineering population this high and at so many systems integrating automatically, you would have a very hard time integrating into the mainline. So we really do put a lot of emphasis on small integration. We even have an internal document called Go Small CLs, which is like Go Small Pull Requests. It's actually public, so you can search for it. And basically, we're always trying to integrate as a series of small changes rather than just one big change. And this is like very important while working at Google. Another thing is code reusability. Like when you've got that much code, it becomes very hard to actually reuse code from various parts, from various projects, and like it had to be addressed in some way, right? Because the usual way I was seeing people and teams managing projects like outside of Google was to have like multiple repositories. Each repository would have like code for, I don't know, specific component or something versionable, and they would expose new artifacts new and then with new versions. This would be very hard to work with when you are at this scale. So we actually addressed it differently. But yeah, we'll talk about this in a second. And yeah, the problem number 3 is tests. So we run a lot, and I mean a lot of tests. So at Google, testing is like something which is practiced like ubiquitously. So like, it's being done by everyone, almost everywhere, and at almost every layer, right? So this means that there is this very strong testing culture at Google, and we are actually not trying. Well, we're not really letting in changes which are not tested automatically. We're trying to do that, and another interesting thing about tests, because when I was doing this presentation, I was thinking mainly about finding bugs. But when I was discussing with other people, we also discussed the value of how those tests allow us to not step on each other. So again, this is because there are so many teams, so many people, so many projects, and so much code. It's very easy to actually break someone if you're not careful, and it's not something that you can change. It's not something that you can possibly verify manually. So being covered by testing is your only safe option of actually maintaining, making sure your new code artifact actually works, that you are not breaking some project on the other side of a company. So yeah, basically this means that we've got a very high load of tests, and this is again somehow related to performance, but I'd say it's a challenge per se to run those tests, because they come with different challenges depending on what kind of test you want to run. If you run unit tests, that's one thing. If you want to run integration tests, that's another set of challenges. So yeah, it's really interesting how Google solves those problems and has several subsystems to actually deal with tests. Okay, so the solutions. So I'm going to discuss briefly the solutions that we deploy at Google. It's not going to be very, shall I say, deep. It's more of an introduction of what they're doing and why we're doing things this way. Yeah, so first of all, let's start with the main solution, which is like the culture, like of maintaining excellence, right? So I've pointed out a few things that I think are really important, and I'd like to go through them. So the first thing is about integrating small often. So this is what we've discussed previously. So again, small changes are so much easier to integrate, but it's not also about integration, it's also about the review. So we have a very strong review culture at Google. It's very common for each small change to be widely commented by the reviewers, and the small changes are so much easier to reason about, because the mental capacity that you need to review a small change is much smaller than for something which is bigger. And if you've got something which is bigger, you can probably split it in a series of changes, right? And the series of changes, if you do it like step by step, it's much easier to look at it. It's much easier to spot bugs. So yeah, that's why we're really striving hard to do those small integrations. Again, in case a change is rejected, this can happen, then less work is wasted, obviously, because of a change which is smaller. And last but not least, it's simpler to roll back. So if you've got a change which has broken, I don't know, tests or some project or whatever, rolling back a small change is always simpler than rolling back a whole feature. Like it's directly a consequence of the fact that when you integrate in 60 seconds, probably there is someone already building artifacts with your new code. And like, this is so important that we integrate just as much as we need. And if we roll back, then we roll back just as much as we need. And that's why there's so much emphasis. Personally, I had a lot of trouble moving to this model, but I have to say, like, after working like this and being set to like split into smaller parts, that it's just superior to integrating bigger changes. And actually, even if I do something like I don't know, in my free time, I tend to like do small things instead of a big feature. Okay, testing. So we covered this part too as well. First of all, testing allows making sure things work at scale. If you test and I don't know, you change something, you can make sure that you are covered. You get a signal before you are actually integrating, so you're not breaking a lot of people around. So this is very useful. And again, this is like this is really non-negotiable thing. Like I think at Google there's no such thing as like integrating without testing. Like it would be not only like it would be like a problem, like that the reviewer wouldn't let you integrate without the tests, but I think personally as an engineer you will have a much harder time if you're not doing tests. They're providing really big value in making sure that whatever you're doing is not breaking not only your project but possibly other code artifacts across the company. So ownership, and another interesting thing. So at Google, we basically have this philosophy: if you write code, you write tests, and that's it. There is no no delegated person to write tests, no automated test engineer or someone who I don't know is delegated explicitly to like writing tests for your changes. If you write a change, you test it. You own the change, you own the test, because you as an engineer, you're supposed to own the fact that this change works and integrates well. So delegating it to someone just wouldn't be practical. And yeah, and as I mentioned, the consequence of this is that by default in Google culture is that we require changes to be tested. Like if I do a change today to production code base and I don't write a test for it, or it's not covered by tests, then it's going to be 100% rejected. There is no way I'm going to integrate it. Okay, so keep things fast. This is rather simple and obvious, but if things run fast, you don't get blocked, right? There is no micro blocks. If you can build fast, you can iterate fast. It's much easier to work with. It's much less frustrating, and you as an engineer waste way less time. And this is especially important considering that at Google, again, we've got a lot of code targets, and building all of those like from one machine would take a lot of time. So we employ several strategies to like speed things up, and we're really keeping those build times to the minimum possible. And last but not least, automate. So this somehow relates to tests, but not only. It's a bit more of a broader perspective. It's that if something can be done by automation, it should be done by automation. So thing is that really important thing at Google that I've learned is that doing things manually is not going to pull you very far. Like it's just too big. It's just too much. So you really need to cover yourself. And I think the really important part here is that the testing is one thing, but deployment, monitoring, I don't know, release scannering, qualification, many things which we're usually doing while trying to get some code into production. It's really important that all of this is automated. It's really important that we as engineers have minimal overhead on working with all the things, right? So that basically this enhances your productivity, right? Because otherwise you'd be stuck doing a lot of very small things which you probably wouldn't be able to do anyways. So so yeah, basically the idea is if you can automate, to automate. Okay, so first, shall I say, implementation wise decision, right? Is that at Google, a lot of things run in as a service model. So I tend to call it everything as a service, which means that Google internally is basically a huge mesh of a lot of various services. And this also connects to the subsystems which are used for, for a development environment, right? So, or development environment, like what we're using for developing software, it's actually some kind of a service which is exposed inside of a company. And this is really interesting because, like, it's sort of like makes my machine, which I use for working with code, sort of a bit of a shell life. Like, I've got a terminal which I do things with, but that's it. I don't really do stuff locally, and this is really really interesting, and actually makes the experience real nice, real smooth, which is even more impressive considering the scale Google works at. So I'm going to walk you through a few of our systems. I'm going to introduce them to you. All of them are already public, but I thought that it's really interesting to hear about them, just to sort of group them into one presentation. So the code. The first important thing at Google, and a very important design decision, Google maintains a single code repository called Google Free, and uses a custom version control system called Piper. So some people might be surprised by this. Some people might think it's very hard to work with, but I assure you this is not the case. It relieves you of a lot of problems which distributed systems have when it comes to integration. So, first of all, there is no such thing as versioning of artifacts in between, in between projects. So, there is no such thing as you've got a project X, which depends on project Z on version 2.0.0. No, this is not happening. Almost everywhere, well, bar some exceptions, we use a single repository. And what that means is that, the mainline, the freshest commit in mainline is the how do you say this word? Authoritative source of truth. So what this means is, if you check out, Google Free repository at specific commit, you've got everything you need to build the freshest artifacts, the freshest code artifacts everywhere. So there's there's no real problems with dependencies, with depending on legacy versions, on some project moving to version 3 or whatever. No, like there's a mesh of dependencies in between, I don't know how many targets, a lot of them. Like, there's like a mesh-like structure of targets depending on each other, and it's all packed in one big repository. So if I run build target X, it's going to depend on other targets in the repository at this version. So one way you could say it is that there's one versioning for everything, and it actually works quite well. Oh yeah, and one important thing, it also means we don't rely on pre-built binaries. As in, as far as I know, like code that is built from our repository is like always working from the source. Like everything is built from the source and can be traced back to every line of code. Okay, so that's one interesting thing. The other interesting thing is the workspace. So we've got a thing called client in the cloud, or for short CITC. So this is how engineers are working with Piper and with code on every day. So how this works is basically there is a system which exposes virtual workspaces for you. So you as an engineer can create such a virtual workspace, and this virtual workspace acts as a window on on the code repository. And you can, I don't know, do some modifications, you can create a commit, you can ask for integration, create a CL or pull request. And yeah, that also means that you don't have to have anything locally, right? Everything is like stored somewhere for you, and you are just like using that view somewhere. I think this is interesting because, you know, like holding things locally wouldn't make sense. It would be very hard to do. Like, I believe it wouldn't be even feasible. So, you know, this sort of solves this problem. This allows, you know, engineers like use the view of the code which is somewhere else, and this is also very helpful because, like, you know, on the side of the workspace, we only hold, like, you know, the changes which are done in relation to the mainline. So, you know, there's no such thing as, you know, cloning the whole repository to everyone, right? So this is in a stark contrast to typical development environment. Like, I don't know, if you work with Git and, you know, you check out the repository, then you know, usually you check out the whole repository, and, you know, you work with this and you commit and you push. Yeah, it's not happening here, right? Like, you've got a view to everything, but, you know, on the other side, there's like just this delta being held against the mainline. So this is one optimization, and you don't have to check out locally, which is also a very useful thing. Okay, so the build, this is also a very interesting thing. Some of you might have used, if you're coding with C++ especially, you might have used a tool open source by Google, which is called Bazel. So Bazel is open source flavor of our internal build system, which is called Blaze. Blaze allows you to expose buildable targets in a declarative way. So you've got, you know, a build file, and you declare, like, you know, there's no imperative, do this, do that, whatever. You've got build rules which say what to build, you know, what are the sources, what are the dependencies, and so on. And then Blaze is able to analyze, you know, the build graph and, you know, start building all of this. An interesting thing is that it is also able, in connection with Forge, to expose distributed build cache. So, you know, if you build some target, you are not really building everything. You are actually just building what you've changed, because if you didn't change things, then, you know, we're going to use the cache. So again, there's like there are savings on the build time, on build computation, and it might sound, you know, a rather interesting thing, like, why are we even optimizing for build computation? Because there is so many builds, right? So we're trying to do that. And you know, you can build locally with Blaze, but usually what people use is a system called Forge, which is a distributed build system. So this is basically what runs the actual build jobs in the cloud. So again, nothing is done locally. Like, when I write Blaze build some target in our repository, it's going to, you know, expose a job to build it. It's going to be built in the cloud. The artifact is going to be returned to me. So for the most part, no things are happening locally. And again, this is coming to all of this everything as a service mindset, right? Because whoever maintains those services can, you know, add capacity, can do optimizations, can do all of the things. Okay, the tests. So first of all, Blaze allows you to run most of the unit tests. I actually even wrote an invocation here, Blaze test some target. So if you've got like a test target and you write Blaze test, it's going to run this test. But to some extent, you could call it like, if you want to run a test like locally, that's like a good way to go. But we also expose two different systems which are used by engineers in various parts of a company, like almost everywhere. So one is TAP. So TAP stands for, I believe, Testing Automation Platform. And what it does is, like, it tests, it does tests continuously on changes, on, you know, on the mainline. So you know, if you've got like some kind of CI system, you know, at your place, and, you know, you are testing each change integrated into master, and you're testing your branches, that's more or less what it's doing, right? It's like like a system which allows you to run arbitrary tests again on the cloud. And it's able to catch regressions. It's able to expose all of the metrics you need for for making sure that you can find the failing tests and at what revision and so on and so on. Another system that we're using is called Pitis, and Pitis is a platform for running integration tests. So TAP is mostly used for tests which are hermetic. It's like I don't know, unit tests or even some sort of integration tests which are like confined to the binary. If you don't need to depend on the other systems. But if you want to run a test which actually integrates with other services, like, I don't know, I've got a system which I want to test against 5 different other systems, then Pitis is really good for that. And the reason is because it allows you to bring up systems under test. So basically, we are able internally to build those systems under test. And when you run a Gitter test, it's able to bring up this system under test. And I can say that, I don't know, I'm bringing up my service and I'm bringing up 5 different services, and I want this to be connected in this way, and I want them to integrate in some way, and then I run the test on this brought up SUT, and that way I'm basically able to do something which is non-hermetic, because again, we're trying to test at every layer, like unit testing, integration testing, and then sort of shall I say end-to-end testing, or something which is not hermetic. Okay, and finally, we've got a system which supports us during reviews. It's called Critique, and it's our internal service to review the changes that we are doing. It allows to do a lot of interesting diffing. It allows you to first of all, it shows obviously the changes that you do when initially you push a change to the reviewer. But I don't know, when you've got some commands and you adjust, and you push another version of your change, then it's also able to show you things like, I don't know, the change was like this and now it's like that. What do you think, right? So it's not just about diffing to mainline, it's can also diff like in between versions of changes, which I think is really, really useful as a reviewer, because you can see like the progress being made. You don't want to necessarily review again from the mainline. So yeah, I suppose this is a really interesting system. One thing which I forgot to mention on the slides, but I also think is really interesting, is that we use a custom IDE called Cider, which is like web-based, as in it's built in in Chrome, and you just open a tab, and we use it it's interconnected to all of our development services, so it's obviously much easier to work with rather than with any off-the-shelf solution. Yeah, okay, I believe we're at 40 minutes time, so thank you very much. We've got, I believe, around 5 to 10 minutes for QA, so I'm giving the voice back to the studio. Thanks.